So let's look at the problem 1. Firstly, we look at the table 4, which are the 4 variables. And basically these variables means like what's the percentage or fraction of change that the reduce the on the reduction of the pollution. So and these are the requirements of the reduction, which is the right hand side of our constraints. And C3 are the 3 constraints coefficients. And this table is the cost coefficient, which is the coefficient of our object function, which we would like to minimize. So for the first problem, like I just told, we formulate this problem. These are from the table 3, and these are from table 2. These are from table 1. And for first problem, we would like to have the fraction from 0 to 1. And then I implemented it in the IBM Cplex. And here is the minimize mod file, which here is minimize, and its coefficient, the constraints are bigger or equal than. And most of this problem, I use this minimize mod file. And on the data file, it's just putting the constraints, the right hand side, and the object function coefficients into it. And let's move on to problem B. Problem B, we don't have to make the xi's be smaller than 0, be smaller than 1. So we originally have like 9 constraints in the constraints. Now we only have like 3 because we don't need the later part of it. And then in problem 3, problem C, we would like to reduce the coefficient of object function by like the solution of the first and the second problem are here. So this is the optimal solution and the optimal solution. So basically, in the B problem, the optimal solution is smaller than the first one. So in problem C, we lower the coefficient of object function by 10%, and then we increase it. So the answer, the optimal solution, it doesn't change, but the optimal object function value is changed, like smaller for 10% and bigger for 10%. And then in problem D, oh yeah. So firstly, we convert the problem into a maximized problem. So basically, I made all the coefficients in the object function, made it into a -1, and then constraints or negative constraints and right hand side. So we can make the the constraint be smaller or equal than constraints. So in here, I use a maximum mod file, and this makes the constraint smaller or equal than. And here is the implementation, and the answer is here. Basically, the same answer as the first question, but with a negative object function. And then for the dual problem of the maximize problem, make the maxima into minimize. Here are the original primo constraints coefficients like 12, 9, 25, and here are the original right-hand side, 3 right-hand sides, and these are the right-hand sides too, because it's smaller or equal than 1, right? So, and here, these are the original coefficients in the objective function, and that's it. So this is the implementation. And the solution of the dual problem, which is a shadow price, and the z star, which remains the same as the primo problem. So for the minimize problem, it's simply like make the primo minimize to the maxima, and the constraints be smaller or equal than, and all the coefficient be the negative one from this dual problem, and the solution will not change. But the object value will be the negative one from this dual problem, because it's one maximize and the other one is minimize. So in problem E, we would like to okay, so any unit change in the constraint, meaning these 3 constraints right hand side, or will like influence the object function. So this is the definition of the shadow price. So any unit of the change in the right hand side of the primo constraint will make this is the solution to the dual problem. So these are shadow price. So we'll make the object function increase by yj. So if, for example, we increase the first constraints right hand side and by 1 unit, and the object function will increase by 0.11105 units. And I implement it in the console, and basically I just input the dual problem into it, and here it shows that how much it can change without change of the without the change of the rate of change in the original problem. So what does it mean? So it asks us to like how much the reduction can be changed without affecting the rate of change in the total cost. So required reduction is the right hand side of the primo problem, which is the object function coefficient in the dual problem, and the rate of change in the total cost is the rate of change is the it's the coefficient in the primo problem, which is oh no, it's the shadow price of the first problem. So it's the solution of the dual problem. So here we just we want to see how much in the dual problem that the coefficient of the object function can change without change the solution of the dual problem, and here is the answer. And in problem F. Oh, so in problem F, we would like to see like how much it can one constraint right hand side can change, and the other one to reverse it. We just basically just make the shadow price divide on another shadow price. And for example, if y1 changed 1 unit up, we want to have y2 change decrease by like 0.876 units. So for the object function, y1 makes it increase and y2 makes it decrease, and they will neutralize. And for problem G, okay, so for problem G, we would like to see like the change of the right-hand side plus the reduce of the cost, which is the tax. So I increase the right-hand side of the constraint and decrease the cost, which is the object function. And the rate of change, the rate of change, which is the shadow price of the sum of the shadow price multiplied by the real change, which is the proportional change. Theta divided by 100 and multiply the sum of the shadow prices. And then we test it out for theta equals to 0, 10, and all the way to 50. So here is a little tricky to implement it in the IBM Cplex. I will show you. So for example, the mod file is the minimized mod file and nothing changed. But here we want to have the theta. So basically, I just add two constraints. The one is theta bigger or equal than 10, and another one is theta smaller or equal than 10. This will like make theta have to be equal to 10. And so theta equal bigger or equal to 10, and minus theta smaller bigger or equal to 10. This is the reverse of the theta smaller or equal to 10. And that's it. So the answers are here, the solutions, and we will see that I think theta 40 has the smallest new object function. So yep, so I choose 40 for it. And then we repeat the ENF for the previous questions, and that's just the same from the one I did in problem ENF. And that's it for this problem. Thank you.